This is my third attempt now, trying to get this video to work. If you hear some background noise, it's my colleague sitting next door to me. The walls here are not exactly thick, so I tend to get a lot of background noise. So this I call a special child in control. I often find this a fired heater. Fired heaters are used to heat mediums or fluids or gases that are entering either distillation columns. Sometimes you see a pump around or a fired heater at the bottom of a distillation column, which is used as a reboiler, or it is a preheater to a separation column or a preheater to a reactor. In essence, what you have is some kind of fuel gas which you burn at the bottom of the fired heater, and you have a radiant section where there are tubes. The tubes pick up the heat inside the radiant section. Now you do get some furnaces where there's cracking that takes place. In other words, there are reactions inside the tubes. This particular example is not one where there's a reaction occurring, because we're just looking at heating, process heating. If there's a reaction that is occurring, there's a whole lot of other dynamics that come into play. This is purely for heating purposes. So you have the medium that you're heating that's passing through the tubes in the radiant section and often in the convective section as well. It looks fairly straightforward. Shouldn't be that difficult. You put more energy in, boom, you get hotter, medium going out. So yeah, it shows you fluid going in, and I don't know why it does that, and the fluid going out. Don't know why it does that. So we're trying to control this temperature here, and this is your inlet temperature, and there's some mass flow that's going in here. Why it does that? There's some mass flow that's going in there. Okay, so this is first thing is we need to set up an energy balance. So your dependent or variable or control variable is the coil outlet temperature. That's the thing we're trying to control. What are you manipulating? It's Q, and you do that through your fuel gas. And your disturbance variable is the mass flow through the coils as well as the inlet temperature. Because your mass flow can change, you might not have a handle on the stream feeding the flow, feeding the gas or the liquid into the fired heater, and the inlet temperature might vary as a function of whatever's going on upstream. So if we just do a mass balance in terms of how much energy is required to heat up to the outlet temperature, that's the outlet temperature, that's the inlet temperature, and there's your mass flow. So this is Q equals mu. I'll put mu as an efficiency, so that's efficiency. And that's your mass flow rate, Cp, which one could assume fairly constant for whatever reason. We've got to simplify it. Now if I take the first order difference, if I change the subject of that equation to the outlet temperature and take the first order difference, you end up with an equation that looks like that. So what it's showing you is that there are three components. Increasing the mass flow decreases the outlet temperature. Increasing the energy in increases the temperature, and increasing the inlet temperature increases the outlet temperature. So we need to try and understand the relationship between the control variable, which is the outlet temperature, and manipulator variable. So the trick is then to divide, ignore these other terms, let's put them out of the equation for now, and find out what the relationship is between outlet temperature, which is your control variable, to your inlet. And if you look at it, you get this relationship down here. Now look very carefully in the denominator. It's the mass flow rate. So everything else is constant for all good purposes. We could assume that that's a constant. That does change, but Cp is typically a constant. But this one here, that one varies. And if I plot that gain, because that's the process gain between the outlet temperature and the inlet firing, as a function of throughput, we get a very nice hyperbolic function. So when you're running your process, you're probably going to be running it around here. So you would tune your temperature loop for this area. During startup, the problem is that your process gain is very, very high. So you are going to not be able to put your temperature loop into automatic because it simply will not control. So you often find people when they start up the plant, operator gets to about this point, some minimum load, and wants to put the loop into auto, and it starts becoming oscillatory, or even I've seen some operators starting over here, which becomes a problem as well. So the question is, well, okay, if we know it's not linear, is there a way to resolve it on the base layer? So okay, if we know that we're never going to worry about turn down and those are not the issues, then we leave it. For a wide range of operation, we need to correct the gain based on load. So what we do is pick a load, so 80% of design, typical operating points, and mark down what is that flow rate at that design point and what is your gain. Then what we do is code inside the DCS or the PLC or the control system an algorithm or a piece of code that at some regular interval modifies the gain used by the PID loop temperature controller based on throughput. So it takes your two reference constants, which is your reference gain and your reference flow rate, and it multiplies it by this ratio here. So if we add 10% throughput, you're going to have 10, and let's say that's 80%. That's 80% of design. So it's going to be 1/8. So you can see on the previous equation, on the previous graph, it would have reduced the gain significantly to cater on the feedback loop to cater for the high process gain. There's some practical issues that you need to worry about. This equation, so this equation just shows you what happens in terms of the PID feedback. I'm not going to go into how, if this is proportional only, you're going to end up with this. So it becomes linear in terms of feedback because I added that gain correction. You just need to worry about certain things that you don't multiply this base value by something that's 0. Interesting why I did that. Okay, I can't undo it. So you want to just clip your, so I typically say, well, I want the gain, let's say the maximum gain is 3, and I don't want it to go below 0.5. So code in some kind of logic to protect you on that. So that's how you resolve. So this is adaptive tuning. And what about the feed forward? So we said there were 3 aspects. It's not just the handle. So we have these 2 other aspects. There's one feed forward component. There's another feed forward component. So the question you've got to ask yourself, if we have a disturbance, what do we need to do to the energy, which is our handle, to keep the change in temperature 0? How do we reject, well, how would one perfectly reject the disturbance? So we set this to 0, and then we solve, and we ignore the one variable in this case, and we solve for how much energy is required to reject change in mass flow. Then we do the similar thing for the feed temperature. So these 2 components have feed forward effects. Now if we assume they're additive, because we did a first order difference and one could assume they're additive, then you have this term 1 and term 2 have to be added together, but they have 2 separate effects. So there's a gain for the mass flow and there's a gain for inlet temperature. Now you'll see the inlet temperature has disturbance that's a function of the mass flow as well, which is also varying. So one would just pass a moving average through the mass flow to achieve this. Now moving average can be achieved with a first order exponential filter, and the window, if the exponential filter is beta, then the time window is can be shown to be a value of 1 over 1 minus beta. So if you have, if beta's very high, let's say beta's 0.99, it'll be 1 over a very small number. So it'll give you a very fairly high moving average window. So that's how you can work out your moving average window size using an exponential filter. So that's how I would filter that. So you don't want the instantaneous mass flow to be used in this inlet temperature. The second thing that needs to be considered, both of these have different feedforward dynamics in terms of lead lag. So they must be passed through separate lead lag blocks. All feedforwards should pass through a lead lag block. Lead lag block looks something like that, and this offset here is your lead and your lag. If your lead time constant is larger than your lag, then you're going to have a higher response like that. So this is how you would solve the tuning for a fired heater where you cater for 2 feedforward effects and for turn down and gain scheduling. So it solves 3 things in one, and it all can be done on a standard DCS or modern DCS system using standard calculation blocks. I realized that I suck at explaining what a lead lag block is, so just quickly found one of my other slides. Best way to, this is an example, this is a lead lag block from the Emerson Delta V, and this is, I think, an extract from a Yokogawa. It explains what shows the S domain or the Laplace transform that's applied, but the easiest way to plot it is just on a time domain, so we'll show you how. Okay, let's try that again. So there's the time on the horizontal axis, and on the vertical axis there's your input signal, and then if you pass that through a lead lag block without any dead time on it, you'll see that there's your, this is if the lead time is greater than the lag time, so you'll have a instantaneous gain of more than 1. So this is the input signal, let's have 1, and conversely that is if the lead time is less than lag time. So your rise time is always based on your lag time, correct. So if you don't have any lead, then there'll be a first order filter, and so we'd normally have a bit of lead, so you have initial gain. I haven't really seen examples where lead exceeds lag unless the signal that's being used as a feedforward is clean. If it's clean, then it's fine. If it's noisy, this is going to make your life pretty special. And that is in essence a lead lag block, and I hope it clears up my very bad explanation and sketch in the previous slide.